Okay, hello everyone. Welcome to Samir's talk today. So I'm very pleased to introduce Samir. He is a PhD student at the Columbia University. Um, he's been also closely working with Ludwig, and he's been part of several projects that a lot of us are familiar with, including Datacom, OpenFlamingo, and so on. So his background has been in robotics, and then language vision, and now language. So I think he has background in many different areas of AI. And today we would learn about his work and his thesis work in how to build data sets to also model scaling and data and designing models. Okay, thank you. So Samir, please take it away.
Yeah, thanks. Yeah, I actually at the beginning of my PhD, I was working with Kiana, so she kind of like taught me how to do research. So it's pretty nice to be back and to speak to all of you today. Yeah, so today I'll be talking a little bit about pre-training and things that I've learned along the way, specifically focusing on dataset construction and also on scaling models. Okay, so I want to start by kind of making the statement that machine learning nowadays is sort of simpler than it's ever been before. Um, and the way that I like to think about this is kind of an analogy to chess, where we have these kind of rules for the game. And once we've decided that these are the rules of how we play chess, there's a lot of exciting exploration to do within the game itself. So for machine learning, if we think of this analogy of rules, we have a lot of common guidelines on how we might build a machine learning system. So we have things like shared infrastructure in PyTorch and JAX, all the way to this notion that scaling a model and scaling a data set is a good idea if we're trying to optimize performance and produce the most performant model checkpoints. So when I talk about converging on the rules, one major part is the training pipeline. So by and large, what we see in machine learning nowadays is starting with some randomly initialized checkpoint, pre-training that checkpoint on some large corpus of data. This could be image text pairs or tokens for some kind of language data set, and then taking that artifact and further fine-tuning it for some domain-specific application. So this could be a specific task that our pre-trained model struggles at, or some kind of other quality that we'd like our model to have, such as being more conversational in a sort of chat application. So pre-training really is the foundation of this pipeline, and we've seen many, many success stories around pre-training. So in the vision language space, we have zero-shot models where these clip type models are really, really good and robust across many different image distributions. In language, we have the emergence of things like in-context learning, where prompting a model leads to improved performance. But really, fine-tuning is sort of this cherry on top to create the most performant models. So I've been involved in some fine-tuning efforts in my time as a PhD student in this Model Soups project led by Mitchell that produced a state-of-the-art ImageNet model, as well as exploring fine-tuning as a tool for continual learning. In the language domain, we also see that fine-tuning is really important, specifically instruction tuning. So taking like this recent Llama 3 release as an example, we can see that instruction tuning on top of these pre-trained models leads to nice boosts in this like MMLU benchmark. Additionally, like in addition to this like high level pipeline, we're also converging on some other kind of rules. So one that I want to look at specifically is scaling. So although we have this pipeline, what we might actually want to do is make it look more like this, where we instantiate a bigger model, a bigger data set, and maybe we want to do this a few more times to where we're kind of completely off the slide and our models are huge and our data sets are really, really big. And this might actually bum out some academics in the sense that the potential for creativity here maybe feels like it's diminishing a little bit. Making things bigger just seems to work. But I'm trying to argue actually that this is really exciting. And because we have these kind of shared parameters around which we can produce better artifacts, it actually allows us to do science with really far-reaching impact, given that experimental setups now look much more similar than they have in prior decades. So in this talk specifically, we're going to look at this first piece of the puzzle, the pre-training piece. And we're specifically going to look at dataset construction and how we might go about thinking about scaling. So the talk is centered around these two key takeaways. The first is I hope to convince you that we should all be doing research on dataset iteration and that this is a key component of the pre-training pipeline that we really need to develop a better empirical understanding of. The second is that we really need to develop scaling laws and understand more rigorously how this process of scaling up datasets and models leads to better performance. So with that, we'll start with datasets. Okay, so one way of looking at the history of machine learning is actually through the development of datasets. So if we look at a case study in computer vision, in the early 90s, we have datasets that look fairly simple, such as MNIST, that just have digits on black backgrounds. But this really motivated the development of things like convolution and some notion that we maybe want to pool features together before we have some classifier at the end. Fast forwarding to around 2012, we have ImageNet, which really inspired a lot of model development. So we get really cool things like residual connections, the development of transfer learning, which are still really critical ingredients in modern machine learning. And then back to just a few years ago, we have these massive image text data sets that lead to things like zero-shot classifiers like CLIP, as well as image generators like DALL-E and Stable Diffusion. So the key thing I think on this slide is that model development and dataset development are really intimately tied, and often dataset development provides the necessary challenges that inspire model development. I've been involved in a few efforts to build better datasets, often with people at AI2 actually. So here are some examples from 3D to synthetic data. But really, when we're building better datasets, we might have this meta question in the back of our minds of what is the right workflow to track progress in dataset development. So instead of just building these ad hoc artifacts for the community to kind of use, we'd like to have a more rigorous process around which we might iterate. So as inspiration for this, we might look at how models are development, how models have been developed over time. So the first step of this kind of process is actually to start with a data set, maybe something like ImageNet or C4 for language modeling, to take some training recipe that we know is good as a starting base, and then evaluate the model that we train on some downstream evaluations that we care about. And critically here in the traditional pipeline, we're going to fix the data set. So we're going to have some monolithic data set that we train on, and we're going to iterate on the training procedure. And this is really great, right? This pipeline has led to a lot of progress, and we have really, really good modeling techniques because of this. Here are just like some examples, but we kind of understand how to do normalization in neural networks, how to initialize parameters. We have really good architectures. But how much performance are we actually leaving on the table by fixing the data set and only iterating on the model? So I think here, like my favorite example of kind of a mislabel in ImageNet is this possum in a shoe that's been labeled as a platypus. And so there's reason to believe actually that by creating better data sets, by iterating on them, we can start to take away some of these mistakes, some of these mislabels, and actually improve the performance of our models. So really having this kind of benchmark pipeline is a really good starting point because we know that it's worked with models in the past. And data comp is basically just that. It's a instantiation of a pipeline for iterating on data sets instead of iterating just on models. So we're going to take this same like 3-step process from before, but instead of fixing the data set and iterating on the training recipe, we're going to fix the training recipe and iterate on the data set. So this is the basic core idea of data comp, and is sort of the key takeaway and the magic of what makes data comp data comp. And specifically, we're also going to fix the evaluation component of this pipeline. And this is really important because ultimately we want to score an iteration of a data set based on the final performance of this data set when things are all said and done and we've trained models. Okay, so data comp specifically targets a type of training called clip training. So I'm just going to briefly go over this so that we're all on the same page. At a very high level, clip training is a contrastive training recipe for aligning image and text representations. So what we're going to do is collect a really large corpus of image text pairs, and the text roughly will describe what's in the image. So by encoding the image and the corresponding caption or text that goes with this image and aligning these representations in some kind of a latent space, we begin to kind of have this multimodal representation of images and text. And the cool thing about this is that at test time, we can create zero-shot classifiers. So what do I mean by this? Well, instead of training a classifier for a specific task, we can actually instantiate a classifier on the fly to do a classification task that we care about. So given some image, we can take this image through our image encoder and embed it as some kind of a vector with d dimensions. We can then write down a list of concepts that we care about. So for example, dogs, frogs, many different classes, and embed those as text features. Again, the feature has this d dimension, and we have n different concepts for our n different classes. And we could really think about the text here as helping us to instantiate a classification head for the specific task that we care about. And then simply by taking a matrix multiplication, we can recover logits or probability that this image falls into various classes. And so this is a really, really powerful paradigm because it allows users to interact with models on the fly at test time in order to do what they really want with these models. Clip models are also really important for other reasons. And here are kind of like a few properties that make them so interesting. One thing that has been of a lot of interest to Ludwig's group that I've worked really closely with is their robustness properties. So they seem to work really, really well across many different image distributions. They're also pretty critical to downstream pipelines that incorporate vision. So I think Flamingo is a really, really cool example of this, where clip backbones are essentially used as tokenizers in order to process images for these kind of image text chat applications. Okay, so now going back to data comp, we have kind of this paradigm of clip model training that we know is pretty good, we know it's pretty powerful, and we want to improve clip models now by iterating on this dataset component. So to really build a benchmark that we trust, we need a common experimental setup. So now let's talk a little bit about how we might go about building this setup that's both reproducible and also general enough to allow a lot of exploration of data sets. So in the beginning, what we want is some really, really large pool of samples. And critically, we want this pool to be minimally filtered in order to allow participants in data comp to explore a broad range of data curation techniques. So a data curation technique might be instantiated as some kind of a filtering algorithm that takes this really large pool and creates a pared down version of it, a subset of it that is high quality in some sense. And once we have this small pool, we can do the downstream training and evaluation in order to get a model artifact that we evaluate on all of these tasks that we might care about. And really, a submission to DataComp is a filtering algorithm. And this is the main piece of iteration that we might want to study. So a key challenge in developing DataComp is actually to build this common pool that we might filter from. So I'm going to talk a little bit about how we did this, just because this is one of the key components that I contributed to in the process and was also one of the more time-consuming parts of this project. Okay, so before we have image text pairs for clip training, what we really start with is URL text pairs. So looking at a massive crawl, for example, common crawl, we have a set of documents, and each of these documents in these common crawl dumps has metadata associated with them, specifically URLs pointing to images and alt text that is associated with each URL. And so we can harvest this across months and months of common crawl dumps to get a bunch of URL text pairs. But there's a problem here, which is that there are many, many duplicates between dumps, and also many different websites might point to the same underlying URL alt text. So we require a deduplication step here to make sure that we're not having a ton of duplicated data. And just for a sense of magnitude, at this stage, we have about 88 billion samples, or 88 billion URL alt text pairs. And just for context, I know many in this crowd are coming from an NLP background, and billion is sort of an outdated term. We care about trillion now. But if we do some kind of back of the envelope math and consider an image is approximately 128 tokens, and captions is approximately 20 to 30 tokens, this is easily a 10 trillion tokens of data. But we can't necessarily download all 88 billion. So we start with some subset of this 88 billion, and we instantiate large servers across EC2 with lots of CPU cores to begin parallel downloading of this data. And here we'll attempt to download around 40 billion, so less than half. And interestingly, we only get even less than this, like only around 17 billion that is successfully downloaded. And you might think, like, what's happening here? And actually, I think this is like some pretty interesting phenomenon. So there's something called link rot, wherein URLs don't necessarily point to images anymore. And so these are kind of like not even downloadable. And also you start to see other phenomenon like throttling that happens. And you want to be mindful of this and respectfully download. So you kind of need to be okay with more than half kind of not succeeding. Okay, at this point we have a bunch of image text pairs, but we have no handle on what's in this data set. So we could have a lot of undesirable, a lot of unsafe content that we don't necessarily want to broadly disseminate to the research community. So a critical step here is tagging. So what we're going to do is we're going to take a really large cluster, in this case, the stability public cluster, which they were kind enough to let us use. And we're going to reserve something like 100 nodes, each with 8 GPUs, so 800 GPUs total. Instantiate some tagging models for key metadata, such as NSFW scores and also deduplication features. And we're going to execute this massively, embarrassingly parallel task of feeding all of these image text pairs through our models in order to tag them. So now once we've done this step, we can think about the metadata and interacting with this metadata, which is really, really convenient in terms of understanding the distribution of data that we have. And we're going to do this for all samples because we want to understand in a distributional sense kind of what is in this whole data set. So I want to go over kind of the key motivation of why we did this tagging a little bit more specifically. So one reason that we might want to do this is decontamination. So recall that we have these downstream tasks and we don't necessarily want people to overfit to those tasks. So what we do in the step with tags is we compute these perceptual features. And by comparing those features against perceptual features for the downstream tasks, we can kind of decontaminate the pool. We also care a lot about safety. So we compute these image NSFW scores as well as text NSFW scores, which we're going to use for pruning to make sure that our eventual pool is safe. We might also care about some notion of the content of the images. So we compute these clip features using pre-trained clip models that essentially will tell us how aligned images are with their corresponding text in the pair. Okay, so now we've computed all of this metadata across our whole pool. And specifically looking at our NSFW scores as well as our perceptual decontamination scores, we can prune down this data set into something that we feel is reasonably safe to train on, or much safer to train on. And this is going to take us down to 13.1 billion image text pairs, which will subsample for a round number of 12.8 billion. And here, like for determining this, we're going to look at a bunch of different thresholds. Specifically for NSFW, we're going to look at commercial APIs and the types of images and text that they might prune and make sure that our pipeline can at least match the performance of these. And a critical thing here is we can always download more images. So we want to be really, really conservative so that we're not broadly disseminating unsafe content. And here I just want to kind of say to everyone that dataset safety is a really, really important and active area. And while I'm really proud of the work that we did in terms of trying to remove NSFW content, I do think that there is probably a lot of improvement to be had. And I'm not going to say that we have completely solved this problem. Okay, so now we have this 12.8 billion pool of image text pairs. It's really large, it's really heterogeneous, but a key constraint for many academics actually is compute. So we want to further subset this pool and instantiate several different tracks of data comp to allow people to participate really at several different compute budgets. And scale has another, having these different scales has another advantage, which is that it allows us to iterate at some of the larger scales to try and only scale up the most promising dataset curation techniques. Okay, so now we have this pool that we took a lot of effort to build. Let's actually iterate on datasets now and get to the fun science of it. So here we realized early on that filtering is one really nice way of iterating on a data set. We have this big pool that we've created to facilitate this. But mixing is another really important strategy that one might have to create a data set. So say you're a researcher and you decided that you wanted to do crawling research, and maybe you think common crawl is maybe really good, but there are other crawling strategies that might help you develop data sets. We want to be able to allow participants to incorporate these other kinds of techniques into their curation algorithms. So we have this more flexible track where we allow mixing of different data sources. But for the sake of this talk, we're going to focus mainly on filtering, which is where we did most of our research for this project. Okay, once we filtered a data set into some high quality subset, we have a training component. And here we're going to take cues from what OpenAI and OpenClip did. Mainly, we know sort of how to set these hyperparameters to get really, really high quality models, and we're going to kind of borrow from what has already been done. Critically here, we're not going to allow participants to modify this part of the pipeline. And this is mainly so that we focus on the dataset iteration component and that this is the only kind of variable that we're allowing. For downstream evaluation, we're going to take a really holistic approach. So we have these 38 different classification and retrieval tasks that we can measure our models on. We're also going to look specifically at ImageNet, the reason being that this is a really important benchmark in the vision community, and we found in our experiment that it correlated pretty nicely with the average performance across these 38 data sets. Okay, so now that we've kind of built the basic tools of what data comp is, I want to convince you that this is a good idea, and that data comp really does lead to better models. And to do this, we're going to start looking at some numbers. So when we started this project, we had this target of 75.5, which was sort of the state of the art for this compute scale for clip models for zero-shot inference on ImageNet. And then historically, we saw there were many different attempts to try and beat this number. So the Lion group created this first data set to try and publicly match this number, and they fell about 3 percentage points short. So at this point, we have really, really good signal that by iterating on data sets, we should be able to actually match OpenAI's number. Lion picked up on this and created larger data sets, instantiated larger models, and eventually were able to beat the OpenAI number. But critically here, they had to really create a much larger data set and also train a much larger model. So to get this 78.5 number, they sort of needed to invest an order of magnitude more compute than OpenAI did originally. So with data comp, we pushed until we actually beat this number with this data comp 1B data set. And in a compute match setting, we beat this original run by 3.4 or 3.7 percentage points. So this is really nice. Like we now have a public model that beats the original OpenAI run. But a more subtle point here is that we actually beat this other Lion run, and we do so with 9x less compute. And this is really cool for a number of reasons. And I think the takeaway here really is that by iterating on the data set, we not only get a model that is better, but also one that is much cheaper to train. And so data iteration really facilitates huge wins, both in terms of performance, but also in terms of efficiency. Okay, now let's talk a little bit more specifically about how we got there. So one critical piece here is having really nice baselines. So we have a bunch of different baselines. On the one end, we could think about not filtering the pool at all. We'll call this no filtering. And here you have image text pairs that are really noisy. So here we have text that just says image.jpg basically, and doesn't really tell as much about the semantics of the image. But then with a clip score filtering type technique, which we'll talk about a little bit more, we get much higher quality samples where we have image text pairs, the text giving things like the make and model of this car. So for clip score filtering, what we're going to do is we're going to look at the similarity between the images and the text, and we're going to create a histogram based on these scores. Then we can have some threshold here, like a 30% threshold, where we're just going to hold on to the top 30% of the pool where the images and the text are most aligned. And we're just going to throw away the rest of the pool and say that this is our pared down subset, which we expect to be high quality. We can also think to do some kind of a clustering-based approach to curating a data set. So by embedding a bunch of samples in a clip latent space, we can take some reference data, which we'll consider high quality, and then look for samples that are in these neighborhoods of the reference high quality data. And so both of these techniques individually might provide some benefits. And what we really found is that by stacking each of these techniques individually, we could actually get even bigger wins. So while each of these techniques on their own may not beat the OpenAI number, by combining them together, we see really big wins. Specifically, DataComp 1B, which is this training artifact that came out of the competition, the first iteration of the competition, is a combination of these two techniques. And I'm just going to flag that, to the best of our knowledge, this is the first data set that is publicly available that beat this OpenAI number. Okay, so we talked a little bit about scale before, and I also want to mention that this was really important for our workflow. We ran a ton of different things at the small and medium scales of our pool and only scaled the most promising techniques to the largest run. And scale is something that will come back later in this talk, so I want you to keep this in the back of your mind. Okay, some other kind of nice takeaways is that dataset size is not the sole determinant of the quality of a dataset. So here what we can do is we can look at various fractions of the pool that we might keep with a curation technique on the x-axis. And on the y-axis, we can look at the downstream performance of the model that was trained. And here we see across several different scales from small to large, that around 30% of the pool is a favorable trade-off with this clip score filtering technique in order to get the best performing models. And a really nice thing here is that this is relatively consistent, especially for the medium and the large scale of our pool, which means that we can iterate at these smaller scales and be reasonably confident that what we're going to see at these smaller scales will translate to the largest scale. Okay, people are already iterating on dataset curation in the context of DataComp. When we initially published this paper, we got this 29 percentage point or 29% ImageNet number at the medium scale. And just to kind of highlight how much progress has happened at this scale from the community, this is now like the 13th ranked data set. So it's been really fun to see this progress. And I think this also drove home to me that we didn't saturate DataComp and that there's still a lot of room for improvement. DataComp is also like completely open source. This was really important to us to make sure that all of the tooling was in the open so that other people could instantiate data comps of their own for maybe different domains that they care about, and continue to kind of develop this high level research methodology of iterating on data sets. Okay, so I'm just gonna quickly go over some key takeaways here from the data set curation part of the talk. The first is that you really want to have an experimental setup that allows you to hit run quickly and train a ton of different models. I think this was really important. We invested a lot in tooling and in an experimental setup that we really trusted, and this really paid dividends throughout the whole process. The second is simply that dataset iteration, I think, is a really, really good idea. As we saw in that teaser result, by doing dataset iteration, we're actually getting like models that are way better and also cheaper to train. Also thinking about curation strategies that are super scalable and that can scale to the largest pools is really helpful. Specifically, simple strategies that maybe are not like super complicated or require a lot of compute to execute end up working really well because they are scalable. And then finally, we can take a bunch of little techniques that on their own maybe don't seem so promising and stack them together in order to build better and better data sets and eventually better models. There were lots of times when we would see things that weren't necessarily heartening, but luckily we didn't give up on them and we decided to kind of combine them with other things, and that was really important. Okay, so now going back to our key takeaways, hopefully I've convinced you that dataset iteration is a pretty good idea. So now let's talk a little bit about scaling. We have a data set potentially that we're excited about. We have a training recipe that we're excited about. Now, how do we scale that to a compute regime that will provide a really, really promising model? So when we think about scaling, I think what we really want to have in the back of our minds is the largest possible run that we have given our resources. And specifically, we don't want to mess up this run. We can mess up at small scale, but we really, really don't want to mess up at the largest scale. And here, I think it's important to think about really large scale runs, maybe that are happening at OpenAI or Anthropic, where we're reaching the threshold where we're investing something like $1 billion or close to $1 billion in these training runs. That's super expensive, and we really, really can't afford to mess up there. So what we really need to do is, based on small scale experiments, we need to make sure that we're going to get a really nice large scale model. So here, we're going to look at these things called scaling laws. And to make sure that we're all on the same page, we're going to go over the basic plot structure of what a scaling law looks like. And this ends up showing up time and again in the literature, so it's good to get on the same page. On the x-axis, we're going to look at the amount of training compute that we invest in a model. And on the y-axis, we're going to look at some notion of the performance of that model. So specifically, we're going to look at some evaluation loss. And here you can imagine, as you invest more training compute into the model, we would expect the loss to go down lower. We're going to consider a few other concepts here. So specifically the number of parameters in a model, n, and the number of training tokens used to train that model, which we'll call d. And intuitively on the x-axis, as we increase n and we increase d, so larger model, more tokens, we would expect compute to go up. So we're going to model compute as a function of n and d. And what we end up seeing time and again in many different experimental setups is this notion of power law scaling. So as we increase n and we increase d, so our circles get larger and larger, loss essentially follows a power law in the amount of compute. So more specifically, we're going to have these two coefficients, lambda and alpha c, that determine the shape of this power law. We can think of the law as a trend rather than as individual data points, and then delve a little bit more deeply into what this power law actually means in the context of our plot. So lambda here is basically the y-intercept in the log-log plot, and alpha c is the slope of this line. So if we have more desirable scaling, this could be modulated by alpha. A more steep slope here would signify a better trade-off as we invest more compute into the model. And power law scaling shows up all over the place. So here are three really famous examples of this, going back to 2017 all the way to the Chinchilla paper in 2022. And I want to call attention to two kind of things in these plots, or really three. The first is that they look really similar. And this is really cool because over a long period of time, several different experimental setups, people are seeing things that look very, very similar. So we have some confidence that this is real, right? The second point is that the trend line that we're seeing is along a frontier. So we'll call this a like a Pareto optimal of sorts. And the scaling that we're doing here, or the lines that we're seeing, are understood in the context of this frontier. The other thing is that the y-axis for all of these plots is loss. So we have this understanding of what's happening on the frontier in terms of the loss. But in practice, many models that we actually care about are not on the frontier. So if we recall this frontier from that plot, it looks something like this. But really what we see in practice is there's a benefit to doing something called overtraining. So here we're going to fix n, so the model size of this smallest model, and we're only going to increase the number of tokens, d. And in doing so, we're going to get this checkpoint to the far right, which is this open circle. It's no longer on the frontier. And specifically, we're going to say that this model has been overtrained in accordance with this thing called a token multiplier, which gives the ratio of tokens to model parameters. So as m grows, we're training on more and more tokens, and we're overtraining this model more. And you might say, why do we care about these overtrained models that are not on the frontier? Well, I think thinking about inference is really critical here. So even though we have invested more in terms of training on the x-axis, the number of parameters is smaller. So every time we run inference with this model, it's going to be much cheaper for our user. And this isn't just intellectually interesting. It's also practically relevant. So for example, a Llama 3B or Llama 3 8E model is incredibly overtrained. In practice, models are also not compared based on loss, so the y-axis, they're actually compared based on downstream performance. So that's like another key drawback related to these scaling laws. So really what we want on this axis is something that looks more like downstream error as opposed to loss. So in this work that I'm going to kind of go over briefly, we try to plug these two holes in existing scaling laws. So first, looking past the frontier in the overtrained regime, and second, looking at downstream error instead of loss. So again, we need a common experimental setup to do this kind of investigation of scaling. And so there we use this repo called OpenLM, which I helped to develop with a few of my collaborators. And it's a pretty simple language modeling code base, which we've been able to scale to the 7 billion parameter regime, and it implements a lot of training tricks and allowed us to really conduct this study. So once we have a little bit of infrastructure, we went ahead and trained 104 different models between 11 million and 7 billion parameters with various amounts of overtraining. And we're going to look at these models and train them on several different data sets to make sure that our conclusions pertaining to scaling laws are not particular to any one distribution. So what this ends up looking like is a bunch of different data points. So here I've shown different models on the y-axis between 11 million to 7 billion, and then ranging with various different amounts of overtraining. So now we have this huge test bed of models. We want to evaluate them. So we'll look at loss on C4, but then we'll also look at downstream performance on a bunch of popular benchmarks such as MMLU, HelloSwag, etc. Many of these end up being multiple choice benchmarks, but we also have generative benchmarks as well. Okay, so now we can start to ask some questions like what happens when you overtrain? So plotting this, we get something that looks like this. And you'll notice that these lines are parallel in these scaling plots. So we might try to describe what's happening here. And by doing this, what we tend to find by kind of rearranging the math is that the amount of overtraining shows up in this lambda coefficient, but doesn't affect the exponent alpha c. And this is really cool and maybe suggests that the line should be parallel, which is what we see in practice. But what we really care about is making predictions with these kinds of scaling laws. So we don't want them to just describe what we see, but actually extrapolate the behavior of much more expensive runs. So now we might ask, does this happen? So to get to the bottom of this, we're going to fit our new scaling form. And we're going to try to predict overtrained runs. So here we train two really kind of expensive, much more expensive models. A 1 billion parameter model trained on about 1 trillion tokens, and a 7 billion parameter model trained on 140 billion tokens. And we see that by fitting this scaling law and extrapolating over 300x in compute, we're able to make these really reliable predictions about the loss performance of these models. But we don't just care about loss, we care about downstream performance as well. And there's prior work that suggests that predicting the error profile of these models is actually a much harder task. But the idea that we have here is instead of looking at per task performance, maybe we can look at the average over many different tasks in order to make some headway here. So now we're going to plot loss on the x-axis and look at the average error on the y-axis to understand if there are any trends. And by looking at our testbed again and plotting these trends, we do seem to notice that there is like a predictable trend here. So we try to formalize this by proposing a scaling law for downstream error in terms of loss. And what this ends up looking like is exponential decay. And we can ask the same question, is the scaling law predictive? So here we want to relate compute to downstream error, and we can do this in 2 steps. We can fit the scaling law from before, and then fit this new scaling law that relates loss and error, chain them together in order to make predictions about downstream error. And again, we can ask, is this kind of useful? Can we make useful predictions? We can take our same test models, the 1 billion parameter and the 7 billion parameter model, and then we see in practice, yes, we can actually do this, but we need to invest a little bit more compute in order to get accurate predictions, suggesting that the average error prediction problem is harder than the loss prediction problem. Okay, cool. So now wrapping up this section of the talk, we have some key takeaways. I'd like to call attention specifically to the importance of developing scaling laws, maybe not just in language modeling regimes, but for whatever regime you care about, and kind of trying to align the scaling theory with the regime of training that you are most interested in. Okay, now just a few parting thoughts. The first is that pre-training is actually really modular. So we looked at 2 pieces of it, dataset construction as well as scaling. And I think that we can hone in on each of these pieces and kind of study them very empirically and rigorously, develop experimental setups that we're interested in, and start to ask some really interesting questions. I also think that for both of these aspects that we talked about, there's a lot of stuff that we really don't understand. So while data comp is a nice benchmark that allows for dataset iteration, uncovering some of the principles about why a technique might work is really promising, I think. And for scaling, thinking about when scaling breaks down and when it's unreliable, I think also tells us a lot of information and is something that I would like to see happen in the near future. So with that, I'd like to thank a few of my collaborators that I put on the slide, many wonderful people that I got to work with over my years of PhD, and I'd like to open it up to questions. Thanks.
This was a great talk. Thank you. I'd just like to ask a little bit, if you could talk a little bit about how you decided on what curves to fit for the scaling laws.
Yeah, for sure. Okay, let me pull up. Okay, so let me make sure that it's still, okay, cool. So for this plot, I think here we were really inspired by the prior work on scaling. So these power laws really show up everywhere, right? So we were pretty confident that what we should see should look like a power law approximately. And then just by having this step of rewriting things in terms of the number of parameters n, as well as this token multiplier m, the math kind of guided us in this direction. So I would say that for this one, we had a lot of like prior work basically to build off of. Specifically, like the chinchilla paper, I think was really useful there. for this scaling law, it was mainly empirical. So I think making this plot was really useful to guide our thinking. But this equation actually does have an interpretation in terms of a power law. So kind of the power law makes its return. Specifically, this exponentiation of loss is basically perplexity. And if you factor that out as perplexity, this is basically saying that error is a power law in perplexity. So keeping with this kind of power law theme, it's sort of fit. But taking a step back, I would say mainly these things are empirically guided, and running a ton of experiments is super important. Yeah, and I hope like this part of the paper, I think, is like less mature in that, to the best of my knowledge, we were the first to kind of report this kind of finding. So I hope to see this more people looking into this and reproducing it, which will give me more confidence, I think, that this is actually the right thing. Yeah, I think it's cool that it shows up. Mm-hmm.
Do you mean, when you say you're the first to report this, you mean this connection between loss and average downstream task error?
Yes. Yep.
Okay.
Yeah, and I think another thing here is looking at many different data sets. So we looked at C4, Red Pajama, and Refined Web for this study, and we tended to see similar things across these data sets. And I think that to me gave me more confidence that this was a publishable result. But yeah, I think yeah, it'd be nice to see this show up a few more times in other papers. Yeah.
So Samir, sorry.
Oh, go for it.
No. Go ahead.
I was just going to ask if you guys, so here, you are just presenting the average error across 19 tasks, I think. Can you talk a little bit about the error on the individual tasks?
That was my question.
Yeah. So error on individual tasks, it sort of depends. I actually have a plot that I can share for this. So there's some tasks where it looks really, really nice, such as HelloSwag. And I think really what this has to do with, like, this is the per task stuff. So you can see that for some of them, you tend to see this exponential decay, like for example, on HelloSwag, where things are very close to random chance performance, and then you see nice exponential decay. And I think really this has to do with whether you're getting signal for the smaller models that you're fitting to. So there is this notion of emergence, and I don't think that our paper is refuting the concept of emergence in language models. It's more like saying that when you consider these average metrics, some of these emergent properties kind of smooth out. But yeah, like I do think that there is a lot of exciting stuff to do in terms of per task prediction, and I'd like to see the science of that progress a little bit further in future work. Yeah.
So Samir, this is very exciting. I want to actually dig a little bit deeper into this, because I agree with you. Like, some tasks are better representative. Like, we all agree that HelloSwag is kind of also evaluating perplexity. So we are curious about other types of tasks. And in your graphs, we kind of see some of them are kind of random, right?
Yeah,
but
for
there
sure.
are some other, like, but there are some other trends that you can see in other data sets. So why did you decide to average over all these rather than picking the ones that seemed kind of behaving better? And then if you had done some analysis on which of these tasks were more representative. So yeah, these are two questions. The third question, which is also related, you said in order to figure out and kind of study this scaling loss at task level, you think you need more compute. Do you think that's the only problem, or like there were other also hidden things?
Yeah, those are great questions. So for the first question, I think we didn't want to get into a game of necessarily subsetting too strongly the data sets. So we wanted to, like, we didn't necessarily want to, like, to cherry pick data sets, we actually do have two different splits. So we look at the average over like a 19 data set subset where we were seeing a lot of signal for small models, but then we also considered the whole 46 task suite. And we actually ended up seeing pretty similar things in both of those cases. So yeah, so I guess we did look at a subset of higher signal evals. Okay, second question was about sorry,
so you answered the first two questions with this answer basically. The next question is about, do you think compute is the only issue for the other tasks that you didn't see much?
Yeah, so my feeling is that this is the lion's share of the problem is compute. So what ends up happening is that a lot of the really small scale models, I think 11 million is a good example of this. So if you have an 11 million parameter model, a lot of evaluations are going to be close to random chance. And if you're fitting to a bunch of models that are all around random chance, the extrapolation is also going to just predict that models will always be at random chance. And we know like one way of getting models not to be at random chance is to invest more compute in them. So I imagine that if you were to go up an order of magnitude in terms of compute, a lot of the things that look random in these plots will look way less random, because you'll pass this point of like emergence. So it would be really cool, I think, actually to do this study just at a larger order of magnitude. Yeah.
Thank you. I think we have time for one more question. Okay.
Well, thanks.
Samir, great talk. Thank you very much.
Thanks for a great talk.
Okay, thanks. See you.
Thank you, Samir.